right, so we want to look at section 1.3, which is new functions from old functions. New functions from old functions. And we're looking at transformations, including things like translation, shifting, reflecting, stretching, shrinking, all those types of things. So they talk about, first off, let's consider our translations. Our translations are when we pick up the figure and we move it somewhere and we set it back down again. All right. So a translation would be like a horizontal or a vertical shift. An easy way to remember this, we talked about in the past, is that any value subtracted from x is going to be a horizontal shift, and any value subtracted from y is going to be a vertical shift. Any value subtracted from x is going to be a horizontal shift. Any value subtracted from y is going to be a vertical shift. So here's how the book summarizes that. They actually give us several different equations. So the first one says if you have y is equal to f of x plus c, that's going to be a shift up c units. All right, here's another way of thinking of that. If I took that plus c is not attached to the x, so it can be moved to the other side. So if I subtract it over to the other side, then I can see that c is being subtracted from y. Any value subtracted from y is a vertical shift. So that would be a vertical shift of a positive c. Positive is up, negative is down. So that would be a shift of c units up. Same idea if we have y is equal to f of x minus c. Again, that c is not attached to the x, so it could be added to the other side. So that would be y plus c is equal to f of x. So I could look at that and see any value subtracted from y is a vertical shift. So negative c is being subtracted from y, so that would be c units down. All right, the next one, I've got y is equal to f of x minus c. That c is attached to the x. It's inside the parentheses, so it can't be moved to the other side. So that would be a horizontal shift of a positive c. And on the horizontal axis, positive is right and negative is left. So that would be c units to the right. And then f of x plus c, that's the same thing as x minus a negative c. So what's being subtracted from x is a negative c, so that would be a horizontal shift of a negative c, or c units to the left. All right. Then we have our transformations. All right. Transformations, stretching, stretching, shrinking, reflecting, things that actually distort the shape of our graph. Now, you know that I live in that house with those three boys that love Transformers, right? So I can't hit transformations without thinking about the Transformers. And literally, that's what a transformation is. It's when you take something and drastically change its shape so it doesn't look the same anymore. So, you know, the car becomes the robot. So we're talking about distorting the shape of this figure. So the first one that they give me here is when I have a number out in front of my function. So if I have a number out in front, like c or 1 over c, we learned last year that that changed the amplitude. That changed how high and low something went. So the textbook calls that, if you have c out in front, that is a vertical stretch by a factor of c. Again, we called that last year amplitude, where we did maximum minus minimum divided by 2. If you have a vertical shrink, that's the same thing as a compression. So a vertical shrink by a factor of c. So if you have 1 over c, that's a shrink by a factor of c. Another way that we talked about this last year, remember we talked about Charlie Brown and Silly Putty? Remember we said if you had like your Peanuts comic strip, and you took your Silly Putty and you put it down on Charlie Brown's face, and you picked it up, then you'd have Charlie Brown on your Silly Putty, right? So we said that when you think of a vertical stretch or shrink, it's like grabbing the top and the bottom of your silly putty and pulling it up and down. You're stretching it vertically. That's a vertical stretch, okay? So that is what we're talking about here. A vertical shrink is when I take that, grab it at the top and the bottom, and it's like I push it back together. I compress it back together. That's a vertical shrink or a vertical compression. So an example of that is what you see down here in the bottom of the screen, where if we had the original cosine curve in red right here, y is equal to cosine x, if we put a 2 out in front of that, that's going to cause a vertical stretch by a factor of 2. So that means that it's like I grabbed a hold of that cosine curve and I stretched it so that it went up and down. So it's stretched by a factor of 2. It is twice as high and low as it was before. If I have 1/2 out in front of that, that would be like the second type here, the vertical shrink. That's a vertical shrink by a factor of c, a vertical shrink by a factor of 2. So that's like cutting it in half. It's only going half as high and half as low. It's going up to 1/2 and down to -1/2. All right, the next thing that they talk to us about is horizontal stretch and shrink. In a horizontal stretch and shrink, that's where we change our period. So a couple of ways that we talked about this last year. This would be like if I got my silly putty again, only this time I grab the right and the left hand side of the silly putty, and for a horizontal stretch, I pull it out so it makes it longer, so it makes it more like an oval. Or for a horizontal shrink, it's like I'm pushing back, my hands pushing back towards each other, so I'm compressing it. When we talked about it in terms of period, we said that your new period would be your original period divided by your B value, where B was the number of complete cycles that you would put in the same amount of space you normally put 1. All right, let's look at an example. Let's come back to the cosine curve. So here's the cosine curve down here in red again. If they gave me y is equal to cosine 2x, that 2 in the middle of that problem is going to cause a horizontal shrink by a factor of 2. We thought of that 2 as our B value, where we said, okay, my new period is going to be the original period divided by 2. For sine, cosine, secant, and cosecant, the original period is 2 pi. So if I do 2 pi and divide that by 2, that means I have a new period of 1 pi. So that means that I've got to be done drawing that entire cosine curve by the time I get to 1 pi. That idea of a horizontal shrink. So you can see that in blue down here, I have the whole cosine curve done by the time I get to 1 pi. It got shrunk. It got compressed. Another way of thinking of that was that B, in this case 2, is the number of complete cycles that I have to put in the same amount of space that I would normally put 1. So we could go through and say, okay, normally I would have to have one of these done by the time I get over here to 2 pi. Now I have to put 2 in that same amount of space. So there it is. There's the first one, and there's the second one. So whichever one of those two ideas makes more sense to you. All right. The horizontal stretch by a factor of c would be something like y equals cosine 1/2 x. If I think about it, I'm going to take my original period 2 pi and divide it by 1/2, so that would give me a new period of 4 pi. So that means that I have to be done drawing one complete cycle by the time I get to 4 pi. That means it's been stretched out. It's been elongated. The other way to think of it is that I'm going to put half in the same amount of space that I would normally put 1. So normally by the time I get to 2 pi, I have the whole cosine curve done, but I only want to put half in that same amount of space. So there's half of it. And to do the other half would take me over here to 4 pi. Okay? So again, when we're calculating this idea of the new period, we need to know the original period. For our trig functions, remember sine, cosine, and their reciprocals, secant and cosecant, have a period of 2 pi. But tangent and cotangent are different. What's the period for tangent and cotangent? 1 pi, right? All right, the other type of transformation that we sometimes see is a reflection. And there are 2 different types of reflection. If you put a negative out in front of the entire function, that causes a reflection in the x-axis. If you put a negative just in front of x and plug that into the function, then that causes a reflection in the y-axis. And we'll see that in just a minute in an example that we're going to work out. I'll point that out to you. Now, when we're talking about transformations, we said that a transformation is something that changes the shape of your graph, very much like, the car changed into the robot type of thing. It reminds me of Romans 12:2. Romans 12:2 says, don't be conformed to this world, but be transformed. As Christians, we are supposed to look as different to this world as that car does to that robot. We are supposed to be radically different. We are supposed to be transformed. As opposed to being conformed to this world, where we let the pressures of society and peer pressures conform us into this little cookie cutter mold of what it takes to be popular and what it takes to be accepted and to just fit into the crowd and go along with the flow. So the Bible says, don't conform to this world, but be transformed. Be totally changed. Look totally opposite of what everybody else does. Okay, great. How am I supposed to do that? The rest of that verse says, by renewing your mind, by focusing on the things that are really important, by spending time reading your Bible, by spending time in prayer, by focusing on whatsoever things are true, whatsoever things are just, whatsoever things are holy, whatsoever things are pure. Think on these things. By thinking about what is going to matter 10 years from now. In light of all of eternity, what am I doing today that's really going to make a difference? What am I stressed out about today that really, in the grand scheme of things, really isn't that big of a deal? So, renewing our mind. All right, last type of thing we want to look at that will be a way to change our graphs is absolute value. So, when we talk about absolute value, we've defined absolute value before, where we've said if you have the absolute value of a function, if what's inside those absolute value bars is greater than or equal to 0, you're going to get exactly what you started with. But if what's inside your absolute value is less than 0, meaning it's negative, you're going to have to get the exact opposite of what you started with. So basically, when I'm graphing that, if you look again at this red sine curve down here, if I were thinking of that definition, over here, this piece, cosine curve, this piece of the cosine curve is positive. If I take the absolute value of a positive, I get exactly what I started with. So that piece of the graph would remain unchanged. Same idea with this piece of the cosine curve. This piece is positive. So when you take the absolute value of that positive piece, you're going to get exactly what you started with. So that piece of the graph would stay the same. However, this piece of the graph that's down below the x-axis, that piece of the function is negative. So when you take the absolute value of a negative, you get the exact opposite of what you started with. If you take the absolute value of a -1, you get a +1. If you take the absolute value of a -1/2, you get a +1/2. If you take the absolute value of -1/2, you get +1/2. So in essence, that whole piece would move up above that axis. And we saw that before in a previous problem where we were working with the sine curve, where we ended up with something that basically just looked like the positive piece and then the negative piece came up and the positive piece and the negative piece came up and the positive piece and so on. Okay? So let's look at an example. In example number 1, they tell me if you have y is equal to the square root of x, so that's our root function, look at the different transformations that would occur given these alternate equations, right? So we look at the first one and they give me y is equal to the square root of x minus 2. Is that negative 2 grouped with the x, or can it be moved to the other side and grouped with the y? It can be moved, right? So if it can be moved to the other side and grouped with the y, what is it going to cause? A vertical shift, right? So we're going to have a vertical shift because we could move that negative 2 to the other side, add it over, and we would have y plus 2, all right? So that would be a vertical shift of a negative 2. So literally, I'm just going to go vertically down 2 and draw the exact same figure. Doesn't have to be perfect, just a sketch. All right, how about the next one? What's that negative 2 going to cause in the next one? Horizontal shift. That one is grouped with the x. Do you see the difference there? Where this one is not under the radical, so it can easily be moved to the other side, but this one is under the radical. It's grouped with the x. I can't move it to the other side. Okay, so that one's going to cause a horizontal shift of what?
2.
Positive 2, right, because positive 2 is what is being subtracted from x. So I'm going to go horizontally a positive 2 and sketch the exact same graph. Now, remember we talked about reflection in the x-axis and reflection in the y-axis on our previous slide, and I mentioned that we would have a really good example of that. Here's a good example of that. We said that if you put a negative out in front of the entire function, that would cause a reflection in the x-axis. So that's what that looks like, a negative out in front of the entire function. So I'm going to take the original function and just reflect it in the x-axis. Skip over to this last one down here. If I take a negative and I put it in front of x, and then I put that negative x in the place of x and I plug it into the function, that is what it would look like. So again, negative out in front of the whole function, negative just in front of x plugged into the function in the place of x. That's the difference between the two reflections. So of course this guy is reflection in the y-axis. So again, I'm going to take my original function and just reflect it in my y-axis. All right, so if we go back to the one we skipped, here's the one we skipped just a second ago. What's that 2 in that function going to cause? Vertical stretch, right? So vertical stretch by a factor of 2, amplitude change, however you want to think of it. So we're going to stretch this by a factor of 2, meaning it's just going to go twice as high and twice as low as it was going before. So I'm doubling each of those values. All right, look at example 3. For example 3, they ask us to manipulate the sine function. So for the first one, they give me sine 2x. So what's that 2 going to cause? Yeah, it's going to change the period. It's going to cause a horizontal shrink. Exactly. So it's going to cause a horizontal shrink or a horizontal compression by a factor of 2, and it is going to change my period. So let's think about what that new period would be. My new period is going to be the original period, which for sine is 2 pi divided by my b value. So my new period is going to be 1 pi. So if this is my normal sine curve, I have to be done drawing that thing by the time I get to 1 pi. Or another way to think of it, since b is 2, is I'm going to put 2 in the same amount of space I would normally put 1. So there I'm done drawing 1 complete cycle by the time I get to 1 pi, or I have put 2 complete cycles in the same amount of space I would normally put 1, whichever makes more sense to you. All right, look at the next one. For the next one, we have a couple of things going on. Y is equal to 1 minus sine x. Is that one being grouped with the x or grouped with the y? The y. It can be moved over to the other side. So that would give me y minus 1 is equal to a negative sine x. Now, I've not seen this in a math textbook, but we talked last year about the fact that there is a definite order in graphing, that if we don't follow a particular order, that we won't get the right graph. And I'll show you that in just a second on this function. So that order that we established last year was we need to horizontally shift first, then reflect, then vertically shift. It's easy because it goes in alphabetical order, HRV. So do we have a horizontal shift here?
No.
No. Do we have a reflection? Yeah, we have a reflection in what? The reflection is in the x-axis, right? So let's take our normal sine curve and let's reflect it in the x-axis. Then, do we have a vertical shift? What's your vertical shift going to be? Up 1, right? So vertical shift of positive 1. So following that order, let's take our regular sine curve and reflect it in the x-axis first. So that would give us this blue graph. And then we're going to vertically shift that. So we're just going to bump it up 1. So again, if you want to take those 5 key points that we usually use for graphing the sine curve and just bump each of them up 1. So like I could take 0 and go up 1. I could take pi over 2 negative 1 and go up 1 to 0. I could take pi 0 and go up to 1. I could take 3 pi over 2, 1 and go up to 2. And I could take 2 pi 0 and go up to 1. And that would give us that vertical shift. So that green graph is our final solution. Now, if we think that the order really doesn't matter, look what would have happened on this problem if I had gone in the reverse order. I did the exact same things. I did a vertical shift of 1 and a reflection in the x-axis, but I did not do them in that order. If I started with my sine curve and first I took that sine curve and I went up 1, so there's my vertical shift of a positive 1. And then if I take that blue shifted graph and I reflect that in the x-axis, this green graph would be my final answer, and that is not the right answer. If you put y equals 1 minus sine x into your calculator, you're going to get this final answer. You're not going to get this final answer. So order does make a difference in the way that we graph these. Okay, one more example, example 5. We have already done something like example 2 and 4, because again, they're assuming we did not do the appendices in the back of the book. So they go through and they talk about sketching parabolas and different ways that amplitude can affect your graphs and that type of thing. So we're going to look at example 5. So example 5 says sketch the graph of the function y is equal to the absolute value of x squared minus 1. Well, to begin with, we need to graph x squared minus 1, and then we can worry about dealing with the absolute value of it. Okay? So let's start with y is equal to x squared minus 1. What is that minus 1 going to cause? Vertical shift of down 1. Good. So that 1 can be moved to the other side and grouped with the y. That would be y plus 1 equals x squared. So we know y equals x squared is the parabola centered at 0, 0 that opens up. And so we're going to vertically shift that down 1, or vertically shift it a negative 1. So we'll draw that parabola vertically shifted down 1. So now that we have the graph of y equals x squared minus 1, now we can sketch the absolute value of that. So we said for absolute value, the absolute value of a positive is exactly what you started with. So this piece is positive, it's going to stay there. This piece is positive, it's going to stay there. But the absolute value of a negative is the exact opposite of what you started with. So I could say, for instance, the absolute value of negative 1 is going to be positive 1. This piece down here is going to come up here. So my final graph would be this thing that kind of looks like a funky W. So the positive piece, the negative piece that got moved above and then the positive piece. All right, so here is our homework for tonight. On pages 46 to 47, we're doing 1 through 5 odd, 13, 19, 21, 24, challenge number 6.